Hello everyone, my name is Matrosov, and today I will be represent efiXplorer team, which is actually Andrey, Yegor and Philip, and today Andrew and me will be presenting our research which we did a couple of months before this conference. So basically, our talk is about hunting for UEFI firmware vulnerabilities at scale with automated static analysis. We try to provide the tool which is powerful enough to find the potential vulnerability patterns with static analysis in collaboration with IDA-Pro and Hexrace. So in the past, I am already present with Eugene Rodionov, Gabriel Barbosa, and Rodrigo Branco the research about distributing reconstruction of high-level intermediate representation for large-scale malware analysis. We did malware analysis at scale, and we analyzed the patterns which has been reconstructed from Hexrace decompiler and IDA-Pro. It's been presented in 2015, and we learned a lot how we can scale IDA for the analysis. In this research, actually, we'll be focused on vulnerability research and how we can scale the plugin based on IDA-Pro and Hexrace decompiler to gain some power of the static analysis to reconstruct interesting vulnerability patterns, which we'll be talk about today. So we will start with motivation and how our automated vulnerability search is working, where we cover the methodology and few very common vulnerability patterns like SMM callout, get variable, and get variable for SMM, and not really frequently discussed get variable inside the platform initialization stage. And in the end, we will demonstrate the statistics by vendor, and actually all the images we analyzed in this research been pretty recently released in this year. And of course, we have a lot of plans to continue this research and develop new functionality for efiXplorer. So let's start what is actually efiXplorer. efiXplorer, it is an IDA-Pro plugin, which is helping to reconstruct UEFI-related data structures and interfaces. If you look on this slide, you can clearly see it is some complex type like a structure, but it's unknown for this environment, and it's why it is not recognized by this disassembly listing. But as example, with Ghidra, you have plugins like UEFI or the firmware utils, which is add to local type database, sometimes related to UEFI environment. It's create much more understandable and useful analysis and reconstruction for UEFI binaries. But we want to create not only a helper for reconstructing UEFI binaries, we want to create an environment which will be powerful enough to simplify reverse engineering work for whole UEFI ecosystem. Basically, efiXplorer have three key components. It's UEFI Analyzer, which is simplifying reconstruction of UEFI-specific types and protocols. And we have UEFI Loader, which is actually unified loader for full image of firmware. It's loading to entire IDB, and basically you can analyze with a single IDB the all firmware drivers contained in this image, which is very helpful and much more powerful to analyze and rebuild the cross-reference between these drivers. And of course, finding common types of vulnerabilities, it's very cool. And we implement some static pattern analyzers for particular vulnerability classes and have a lot of interesting ideas how we can improve it with power of hexarrays microcode and intermediate representation like C-trees, especially for the data flow reconstruction. So on this decompiler listing, you can see how cooperation between hexarrays and efiXplorer works, and actually this looks like a real source code file because it's very readable. Most of the types is reconstructed, and you have a lot of hints about this flow, what is actually going on there. But as example, efiXplorer can find automatically software SMI handlers. And without efiXplorer on the hexarrays decompiler stage, as clearly we can see on the left side of the slide, it is a red deck decompiler, which doesn't collaborate with the local types databases inside the IDB, and clearly it's not understandable listing and not annotated enough to make it readable. It's actually why we highly recommend to collaborate with hexarrays with either pro reconstructed and annotated assembly hexarrays decompiler, because it is actually might create much more readable listings on the decompiled flow. But of course, remember to look on actual assembly code, because without understanding assembly, it's hard to spot the mistakes in the compilation. So how it started? So UEFI Analyzer was not, I would not say simple, but much more simpler than we have in nowadays, because we add a lot of functionality for platform initialization stage, which is not very don't have a lot of coverage on other plugins. We added some vulnerability patterns recognition. We added a lot of additional heuristics, and as example for SMI handlers and for CPU state detection, for SMM callouts, and much more. So actually in September we got a third prize of the hexarrays plugin contest, and thanks hexarrays to spot of our potential and usefulness of efiXplorer plugin. We're very proud of this honor, because efiXplorer, it's pretty young project. It just started on the beginning of this year and get a lot of traction, and we get a lot of feedback from researchers who are using it daily. So what is actually motivation for this particular presentation and research behind? So think about, we have the hardware threat modeling, firmware threat modeling, and operating system threat modeling. Most of these threat models is disconnected from each other, and basically as boot process going to the high level stacks on the operating system level, then we gain much more signals for threat intelligence, forensics, and actually threat detection. But if we go down to the stack, it's much less signals exist and actually produced. So we have clearly lack of threat intel and forensics on the firmware level and threat and hardware level. So in our research, we try to fill the gap on the firmware level and give forensic and threat analysts very useful tool for simplify research and save a lot of time. Okay, and the good example actually from the firmware side, it is non-volatile memory. Actually, if you're not familiar with UEFI firmware, it has a NVRAM storage for variables, which is actually very powerful configuration data storage with a lot of information inside. But also it's frequently used by operating system and hardware vendors to store very weird stuff, by the way. But also we know some cases where NVRAM variables being abused by firmware implants. So Okay, and this picture actually demonstrates how boot flow transform access to NVRAM variables. As example, from platform initialization stage, we have access to the firmware, to the NVRAM storage, and it's not actually split between level of access compared to the Dixie phase, where we have the interfaces for system management mode and for the Dixie, for the normal Dixie, and it's separated with the different access privileges. And of course, we have operating system interfaces to get enumerate the firmware variables, NVRAM variables, and actually with direct memory access, you have enough power to basically avoid native operating system interface and understand what actually is missing or hidden from operating system native interface, because sometimes Microsoft and some other vendors try to hide the variables accessible from native APIs. Okay, let's talk about NVRAM as a persistent storage. Actually, NVRAM variables have two different types. It is a runtime storage, when it's stored and accessible during operating system work, and it's only accessible after the system, only when the system is running. But we have a persistent storage on the SPI flash, where the variables is stored and it survives actually a reboot. So in this storage, we have enough variables, which is create some dangerous attack surface. And what is interesting, these regions with NVRAM persistent storage doesn't covered by Intel boot guard and can be abused by the attacker with a physical access, which is make very dangerous supply chain attack vector. And arbitrary code execution over the get variable, it's quite common, and attacker can modify persistent NVRAM storage variable to install fileless Dixie, SMM, or PI implant, which is based on some shellcode and not feasible on the driver level, or basically it's hard to spot during execution or even sometimes runtime forensics. So most security solutions inspect only UEFI drivers, but doesn't look on persistent NVRAM storage, which is create a lot of interesting possibilities for the attacker. As example, platform length variable is quite common case because it's EDK normal variable for language, for choosing the language for the platform. And on this screenshot, we can see the issue where it's basically the size is null, but we can control this size, and platform variable is actually also can controlled by the attacker. We'll be talk about these vectors a bit further, and Andrew will be covered with a lot of additional details. Also, I want to shout out to the researchers which is make some research about make NVRAM runtime persistence not in SPI storage, but persistence enough for hiding from modern EDR solution and endpoints. So pay attention on these links, it's quite cool research there. But also NVRAM persistent storage with the physical access to the target machine was mentioned in CIA Vault 7 leaks before, which is mean this vector is known for years and already abused. Very interesting work actually also will be discussed on this conference in Arsenal session. Pay attention on EFI FAS, because collaboration between EFI FAS and efiXplorer, it's very powerful. And it's actually can used for EFI FAS can used for proof the potential findings found by efiXplorer. But if we talk about the fuzzing, think about limitation of black box fuzzing of a file. Basically, we have a code coverage based on feedback loop with a very limited static corpus. And of course, random input mutations having only initial knowledge and may need extra reverse engineering work to create more precise and valid corpus, which is actually can be covered by efiXplorer. And platform simulation like CMix with combination of symbolic execution can fill this gap and provide more feedback loop and test coverage in general. So I think Excite project from Intel, where I contribute in the previous years, was very useful in this case. And of course, efiXplorer can provide some coverage and helping with corpus generation for potential targets. Okay, and few words about disclosure. We have ongoing disclosure with Intel, where NVIDIA offensive research discovered multiple vulnerabilities with get variable on different levels, but it's take a while, and this disclosure date will be something in April 2020, and I hope soon we can discuss more broadly these issues, maybe on the next Black Hat. Thank you, and I think, Andrew, it's your turn. Continue this presentation. Thank you very much.
Hello, my name is Andrey, and I will talk about efiXplorer and its automated vulnerability search capability, and how we did it to make sure that it works well at scale, and how we make sure that our methodology is kind of sound to the best of what we can do. First, let's talk about the data sets and the type of data we collected. We have ISROC, about 400 of firmware images. We have ASUS, and a little bit more, close to 1,000 firmware images. And we have Lino, about 84 firmware images total. All of them were released in 2020, which means that if we find the security issues there, it's likely valid and it exists, and it's pretty much of a concern for users which rely on that product. We use 3 types of measurements in order to understand how well is efiXplorer doing its job. First, we measured object recognition, such as boot services and runtime services. If you want to get more information about how we measured basically that fundamental components recovery, how well is efiXplorer is doing its kind of baseline things, you can take a look at our EcoParty presentation. Let us know if you have any feedback. Reach out to us, and feel free to investigate and inspect it if you want to get additional information about our measurements. This part is unfortunately a little bit out of scope of this research. 2 things at the bottom are in scope of the research: measuring attack surface and running automated vulnerability scanners. We will present those numbers later, and this is what we collected for all of the vendors, and this is what we collected per phase, per boot phase, such as DXC, SMM, and platform initialization. Now let's talk about each vulnerability pattern. We start from SMM callout. This is a well-known attack vector. It's well-known for years, and it unfortunately retains its significant place in the security audits. It's well-known, unfortunately, or hopefully, depending on your point of view. To understand what it is, you should know that there's my handler. This is something, kind of a function handler, part of the interface, communication interface between operating system and the SMRAM. And if a code inside SMM tries to dereference the DRT pointer or GBS pointer, bad things can happen for one reason. Those tables do not guarantee to exist after the exit boot services is called. And basically this memory is under control of the attacker. If we assume attacker is, for example, coming from an operating system and trying to escalate privilege to ring -2 or whatever you call it. If this happens, then this is a vulnerability which attacker can take advantage of. How do we find it? This more important question, how do we find it statically? Well, we just iterate through all of the SMI handlers, try to find all the references to those variables, and once we find it, we flag it for the manual review. It sounds like relatively simple, but that requires a lot of static analysis beforehand. Here's how the registration of SMI handler is happening inside the firmware. You can see the legit firmware registering SMI handler. So it's just a matter of calling SMMs of SOA dispatch protocol, then get an interface, and then actually calling a register, where the SOA SMI handler is just an argument. It's a pointer to a function. We are able to analyze those constructs and then extract the argument, and from there we understand that this is an SMI handler. This thing points to a function, which is a function of interest in a way. This is exactly the same code, but in decompiled form. Pretty straightforward. Register, SMI handler. From there we know that this function is SMI handler. Now, how we find vulnerabilities? I would say potential security vulnerabilities there. We just iteratively and recursively go through all the functions from that SMI handler and find references to DRT or GPS, a runtime services pointer or boot services pointer. Question is, how do we know where they are located? Well, it's because the efiXplorer is able to collect them beforehand, and we store them separately, and we just compare whether these is dereferencing actually a memory we know already is marked as GPS or DRT. The algorithms are pretty similar. With one additional step, you can also get the same information for the whole image versus just for a single driver. We can use the efiXloader, which iteratively goes through all the drivers and does the same thing. And from there, you get SMI handlers from the whole firmware. What's new and what's interesting there, compared to what existed before, is that we do that statically without running firmware, just by having a firmware dump. Another way of doing that is, for example, to find a vulnerability, let's say in SMI handler or in whatever, and then execute code in SMRAM and then take an SMRAM dump, extract it, and find SMI handlers from the memory. We approach the same thing, but slightly from a different perspective. Just we do that statically, and it works. Speaking about the numbers, I would say that Lenovo is actually relatively good at attack surface. The average number of SMI handlers per firmware in case of Lenovo is only 20, but iSRock and Asus are slightly worse with respect to that metric we chose and with respect to how we collected. And Lenovo is also relatively good with respect to a metric of the number of potentially triggered SMM callouts. However, we found a few interesting things in our datasets. We still work on that vulnerability. It's in the process of disclosure, but it's a straightforward callout. This is SMI handler from one of the firmwares. It uses a read save state to read registers which are controlled by attacker. And then depending on the values of the registers, there's a lot of code we just skipped because there's a very long switch statement, and once it goes inside inside one of the locations, depending on the value of V45, it just mistakenly tries to dereference GRT. It's probably code which might have been forgotten or maybe left by mistake or something like that, but there's nothing great in that. Let's talk about get variable patterns. We investigate this situation from 3 angles. We try to understand get variable calls from the SMM phase, from the Dixie phase, and from the platform initialization stage. And later we will tell how different is the situation at all of the boot stages. And of course, this attack vector and security vulnerability is well known for many years, but we just try to investigate something which is still valid, still relevant, and try to understand and infer some information about how vendors are doing and what is the state of the security in that regard, and if we try to cut it in that dimension. So before we go to the explanation of our vulnerability checkers, let's take a look at the get variable. Get variable is the standard EDK2 library code. You can find it freely just by going to EDK repository. One slight thing which might be not immediately obvious or might be misunderstood sometimes, somewhere, it is that this function takes a few arguments, including data and data size. Both of them come as pointers, and data size is a pointer which is updated even if the data is not being copied. In a case if the function tries to get environment variable and then sees that the environment variable is larger than the value of the data size, which is being supplied as an argument, it returns an error, yes, but at the same time it updates the data size, and that thing might not be immediately clear to in some situations in a way. And using that information, how do we find potential security vulnerabilities? Well, we just started from something simple. Let's just try to find sequences of two get variables in a row which use the same data size and which is not initialized, and see what it yields us. And surprisingly, this pattern works pretty well. We were able to find a lot of interesting things in our data sets. Here is the output of our static analyzer. You can see where the condition is met, condition consisting of three different things. When all of them together are true, a static analyzer returns a result for us for a later manual investigation. This is an example of what could possibly happen. Well, not quite possibly. Sometimes this is what actually happens in the firmware, like in this case. There is a data variable, straight statically sized data on a stack, and there are two get variable calls. One of them calls tries to get a value of the environment variable, then it checks that whether UEFI buffer too small is returned, but then it never checks that the updated data size is actually smaller than the actual amount of data which is allocated on the stack for the data variable. If this variable is controlled by an attacker, then this is going to be a very straightforward buffer overflow. Speaking of security, speaking of exploitation primitive, this primitive is pretty much powerful because it allows stack overwrite, and the length is controlled and the content is controlled. Something which does not always happen, and when it happens, it gives a lot to an attacker. Here's what might also go wrong when the same data size is being used to retrieve the values of two different variable names. And if this data size is not reinitialized, and then if also there is no logic which would skip all the later processing and stop all the later get variables when buffer too small is returned, then the bad things can happen. So the first call will implicitly update the data size, will not do anything, but the second call will actually do something useful for an attacker and something dangerous for the end user, and maybe something not very interesting, not very exciting to investigate for the vendor. I mean, speaking easily, this is going to be security vulnerability. If we talk about numbers, I would say get variable in its initial straightforward form and Dixie stage as a part of runtime services table. Speaking of that, the attack surface is quite large. I would say it's quite massive. IceRock, Asus, and Lenovo has a massive number of calls at the Dixie stage. Lenovo is slightly better at the attack surface if you look at this metric, but it's slightly worse than IceRock and Asus if you take a look at the metric of a number of potential security vulnerabilities triggered by our static analyzer. I'll be straight here that this pattern, of course, is like any of our patterns requiring manual review. So not all of them are immediately exploitable security vulnerabilities, but a lot of them, when we triage them, turn out to be pretty straightforward security issues indeed. Not all, but many of them. The example we show here is, again, straightforward, almost textbook buffer overflow. This code is taken from one driver which belongs to one of the vendors. The data here is again stack variable, statically sized. This environment variable which is being read is platform lang, and the data size is being implicitly updated. However, no one checks that this data size is actually less or equal than the number of bytes available, than the size of the data on the stack. The same situation with getVariable happens on the SMM stage. There's a special protocol called UEFI SMM variable protocol, and it's just a matter of getting that protocol and then using that pointer to that protocol as a table to table to functions, and then using SMM getVariable function or other functions. Pretty straightforward. Additional step is just to one nested step is to find those interfaces and to understand this is actually SMM getVariable protocol. Once we do that, the algorithm of how we find and check that this is a potential security vulnerability is exactly the same as before. We just see that there is a sequence of two getVariable calls using the same data size reference and the same data size argument, which is not initialized, and see what it yields us. Again, this is the output of our static analyzer. This is an example of what could go wrong. For example, if there is a sequence of two calls which obtain same or different variable names, and this data size is implicitly updated underneath by the EDK library code, and this behavior is not properly handled. This results in a buffer overflow. Whether it's a buffer on a stack or buffer on a heap, in this context, this doesn't matter much, but it just going to cause out of bound write, whatever place the data is allocated at. More interesting is the statistics. We noticed that the SMM, which, as you remember, quite a privileged place, like thinkably, you should probably, as a vendor, should probably protect it. And this is kind of, from that perspective, this is what probably happening, because if we compare that with the amount of getVariable calls on a Dixie stage from the runtime services, the average number, that amount of attack surface, is quite smaller, and the amount of potential security vulnerabilities triggered is near zero. For example, it's, I think, literally 0 cases for SROC, and for Asus it's something like 3 cases per 800 firmware. So it's going to be a few 0.03, I think, something like that. I fully know its average number is about one vulnerability pattern per firmware. As for the results, what we found, this is real code from the real firmware from the 2020 or near that in somewhere in 2020. It is an I think a well-known product, and the situation happening here is exactly as we explained before. There's a data size. It is initialized once, but then this value on a stack is implicitly updated at the first call, and no one checks that this the situation is happening. No one checks that data size is updated, and the second call causes an overflow of data variable. Now, platform initialization stage. What happens with the get variable and how get variable works is kind of very, very similar to what we know from the explanation before. However, this attack vector is, we believe, it's slightly under research, and it works very similar to SMM. There is a PPI, which is also an interface. As a developer, you get that interface, and then you use that interface to call things like get variable and things like that. Again, how we find the security vulnerability related to that? Well, the hard part is to get all of those get variable calls by locating all the places where PII services is used to obtain that interface, and then to transfer that interface somewhere, and then using that interface as a table of function pointers, and then using that get variable function pointer, just calling get variable. And after that, what we do is quite similar. We just use a data size as a marker. We try to find a sequence of 2 get variable calls in a row using the same data size, and mark it as a potential security issue if those conditions are met. As for the metrics, situation is slightly more interesting. There is much less attack surface if you compare it with the Dixie stage, but if we compare that to the number of potential security vulnerabilities triggered on that Dixie stage, the numbers here in the platform initialization stage is actually larger. That means that attack surface might be not so large, but there are many more potential places, which might seem to imply a lot of possible explanations. For example, it might be that security researchers did not actually completely look at this compared to how the Dixie or SMM stage was investigated. Maybe not. Or maybe vendors did not actually look at this place from a security perspective themselves. Or maybe there is another explanation, but this all is restrained and constrained with the metrics we choose and the metrics we use here, and to how we collect those metrics, of course. But again, talking about the results, we were able to find a lot of security issues. They're in the process of disclosure, and this is one interesting example, quite illustrative. The data size is a variable allocated on a stack, and then it implicitly updated after the first call, and nothing or no one checks or maybe handles the situation where this data size is updated underneath implicitly, and there is no obvious check for the error conditions, such as buffer too small, in a way that second call to get variable is being executed as well, regardless of what happens with the data size. Now, as we researched all of those vectors, let's talk about the overall stats and overall results. So we just collected the whole table, and this table is for the whole for the whole range of all attack vectors and all the ways we tried to measure attack surface. From there, we see again that the Dixie stage has a massive attack surface. The SMM stage is kind of well protected, and the PII stage is something interesting. Lenovo is slightly better in some ways, but not in all ways. Attack surface is slightly lower if we talk about the semi-handlers for Lenovo, but let's say in other aspects, such as number of number of SMM get variable calls, Lenovo is kind of a little bit worse in that regard. But however, this again is constrained and restrained to the metrics we choose and approach we use. If we try to summarize all of the results per boot stage, the situation gets a little bit slightly more clear. For the Dixie stage, there is a massive attack surface, and there is a relatively little amount of potential security vulnerabilities. SMM, which is inside important trusted boundary and in kind of a place relatively privileged, is kind of relatively protected, but the PII stage is not entirely researched and seems to be like a good place to dig into, because the amount of potential security vulnerabilities triggered with regard to get variable related to its attack surface is quite larger than, for example, in Dixie stage. So the platform initialization is something where I would suppose we might look further and find something interesting. Now, let's talk about future plans. All of our patterns have one thing in common. They are bound pretty much to the assembler, to how we find the patterns in assembler and how we handle different flavors of code generation. We are able to do that, and it actually works, and it works pretty well if we tune our heuristics very well. And we do that, for example, just because for UEFI there are not so many compilers. A lot of build pipelines rely on I think Microsoft Visual C++ in order to get authentic code or something similar to that. There's no such diversity in compilers, and so there is more from a statistical perspective, more stable, more stationary picture. If we talk about how what is the distribution of different code generations or different code patterns resulting from different compilers. But then, however, it presents a problem. And one of the problems is that we're not able to fully offload things we're not good at, and those things are understanding what are the arguments of a function. There are so many calling conventions. There are potentially so many architectures, and even with this restrained number of compiler generation options, there is still a lot of things we cannot handle in general case. Let us just offload it to the disassembler and its intermediate representations. They are built for that, so it seems to be a very natural next step for us. Let's take a look at the code. Same code, which on the left side looks in a disassembly form, and the right side it looks in a form of a microcode when it's being translated to an intermediate representation. Slightly more compressed form is a form of a decompiler. You can see it on the top. What is the most important thing we get for us in terms of automated vulnerability finding? Well, it's arguments of a function and information about the argument, such as length, types and whatever else you can find. Once the type of a table is known, then all the heavy lifting work can be safely offloaded to whatever is doing translation and lifting or whatever optimization and all of the magic, which is intermediate representation, doing well. And then after that becomes very easy to find patterns like that and to write more expressive and more powerful patterns, and basically do not work too much trying to find workarounds of compiler optimizations and low-level specifics. You can take a look at how C trees look like on the right side. You can see how abstract syntax tree looks like. Basically, it's one of the standard things, not very much different from how you would expect abstract syntax tree to look like. There's a block followed by an expression has an assignment, and an assignment has two nodes, data size and some value. This form, hex-raised C trees, is a more high-level representation, and it's very good at data flow analysis, which means it's very good at finding when particular value is assigned to a particular variable, for example. But it's, of course, much more useful to many other problems as well. This is just an example. Hex-raised C trees is not the only way of representing a code in intermediate form. There's also a microcode level, which has been shown in a previous slide. This is more low-level, more, I would say, more intermediate representation, something in the middle between hex-raised C trees and the pure assembly. It is very good in a way that it doesn't go that long to do a lot of optimizations and trying to extract what hex-raised C tree is doing. It's more deterministic, and it works very well for semantical things, for algorithmic things, but a little bit less for the data flow analysis. Now, let's finally go to our conclusions. What we want to say is that for firmware, and UEFI in particular, static analysis works, and the static analysis is based on a bunch of well-tuned and well-understood heuristics, and of course it's also based on a deep understanding of how firmware works as well. And those well-tuned heuristics work surprisingly well for recovery of important structures such as function calls and GRT variables, where they're allocated, where they're referenced. But that's something we already know. What we know now in this research is that it actually works pretty well for also automated attack surface measurement. And it works pretty well for finding potential security vulnerabilities, which also result in real security vulnerabilities. So it's good at automated vuln hunting. Another point we want to make is that firmware vendors probably, if we make some assumption that they did it, they probably did well on attack surface reduction. Or maybe we can just say that attack surface is kind of not terrible in some cases. But still, however, well-known attack vectors, well-known for years and well understood for many years, they still exist, and there's still a little bit of a concern in 2020, even for some vendors which are not, which are considered to be good on providing quality products in a way, but it depends on who you compare it to. Those vectors are the SMI callouts, well-known attack vectors, and get variable, various ways of misusing get variables from a Dixie stage, from SMM stage, and from platform initialization stage. From there, we want to say that despite the fact that we build a thing which works, and we give it to to security researchers. We as a community still need more tools like that, and tools other than that, which would help UEFI security as a whole. We would need open, usable, and working instrument for UEFI. And there is always lack of good instrument for that space. I would suggest that a lot of tools would be quite useful for vulnerability research, for reverse engineering, for automation of those tasks, for forensics, and for data science. There are still a lot of open problems there, and there's still much less instrument to investigate and to inspect what's actually in there and what's hidden there by the attackers, what's hidden there by threat actors, what's hidden there by vendors, and what's hidden there by whoever else we just didn't know. And from there, when we have tools and instruments, when we have more of that, it's about the right time for a much broader audience to take a look at the problem of potential UEFI implants. I would say potential because actually no one knows what's there. And it's about the right time to take a look and try to answer this question, because it's just interesting to know what's in there, what implants might be there. Who knows? This is all. Thank you for your attention and stay safe.